Hello everyone, welcome to Team 34 Interim presentation. Our team members are Edith, Aurora, Ella, Karen, Rochelle, and William. For our project, we chose to analyze a belt and disc sander. As the background of the product, sanders are used to smooth wood or metal surfaces. A motor is used to turn two shafts that spin each sanding phase at high speeds. The vertical belt offers more flexibility, while the disc provides stability to sand the object. Here is the image of the sander.
Moving to our primary and secondary customers, the sander has a product demand of 1.76 million devices annually with a CAGR of 14%. This comes out that the estimated production volume is 80,000 a year. As we analyze the sander, we are taking our primary customer to be the direct users in industry applications. Those would be those in the machine shops, actually using the sanders to shape products by removing the excess material. And then our secondary customer would be university workshops that use the sanders mostly for demonstrations to students and smaller projects led by students. And on this slide, you can see the exploded view of the sander itself with the list of parts on the left.
Now coming to function analysis system technique diagram, the task function is to finish the workpiece either made of metal or wood. Here finishing workpiece involves different types of operations like shaping edges, smoothing surfaces, removing paint, removing excess material, etc. There are two primary functions. One is removing material and the other is to support the workpiece. The remove material function further branches out into basic functions, and then as you can see there are a few supporting functions as well.
So moving on to assembly sequences, the first would be the subassembly sequence, where we start with the base, put on necessary supports at the bottom, and then move on to the belt sequence after putting on the motor, and that consists of table support, tensioners, and then the belts and bearings itself. And then we would move over to the disc assembly, which would consist of the disc mount, disc, and as well as the casings and tabletop there. The next sequence is the ground up assembly, which is pretty straightforward, and this just consists of building from the ground up, starting with the base, and then moving on with the disc mounts, the motor, as well as the disc on the motor, and then adding kind of the lower supports as well as the table, and then moving up in the z-axis to finish off with the tensioner, and then finally the belt. Now for a comparison of the assembly sequences, the subassemblies method has advantages in transferring and handling, testing subassemblies, and assembling in parallel, while the ground up has advantages with locating parts, as well as the ease of fastening and joining when you're assembling in the z-axis. But overall, the subassemblies gets a higher score.
Coming to the function component mapping matrix, you can see the columns defined by the functions on the terminal leaves of the fast diagram and the rows defined by name of all the parts of the products. The matrix helps to know which parts are involved in performing what functions. As it can be seen in the matrix, the highest number of parts are involved in performing the transmit power function.
Here's the first part of our bill of materials for the 32 parts of our product as numbered in the exploded view. Most of our parts are made of steel or aluminum and use water jet cutting, milling, lathing, or sheet metal forming as the manufacturing process. We have some parts and assemblies, highlighted in yellow, that will be purchased from an outside supplier. This is the second portion of our bill of materials. The total manufacturing cost of our product comes out to $1,226, mainly due to material costs. Taking our parts as labeled in the bill of materials, we sorted them into a quad chart based on manufacturing cost and functional importance. We had no parts that we considered to have low functional importance, but a few parts that had high cost that will be considered for redesign.
Moving on to product family design, here we take a look at the FTT diagram. Here we separate the functions from the fast diagram into two groups. A group for the similar functions for the two groups, which you can see on the left, and on the right it's the functions different for the two customer groups, which would be rub wood, rub metal, and transmit power. Now we can take a look at the CCT graph, where we separate the standard components into those that will be the same for both customer variances. That will be on the left, and on the right we'll list those that will be different, creating the modules themselves. These parts include the disc mount, the belt, and the motor.
From our primary and secondary customers, we develop variations for industry and education. Since industry typically uses heavy-duty materials, the industrial variation includes a steel frame, high-power motor and belt drive, and a 320-plus grit disc. In contrast, since educational applications typically use softer materials, the educational variation includes an aluminum frame, system, low power motor and belt drive, and a 120 to 220 grit disc. Based on these differences, there are two common interfaces that can be seen in the subassembly on this slide. The two interfaces can be seen here in more detail. It includes the disc racking on the left and the metal frame on the right.
The product family diagram shows the original version of the product. The original assembly sequence runs parallel. In the modified assembly, the disc mount, top casing, and trundle are selected first. It is difficult to optimize further assembly because the sequence of assembly has to be in a particular order with certain stages depending on completion of others.